My name is Mikael Holmboe. I'm an associate professor here at the chemistry department at Umeå University, and I'm some type of mixed experimentalist and computational geochemist. I like to study the molecular scale of complex minerals, especially sheet silicates and swelling clay minerals. And that's what this up till now working film was showing a little bit. Um, and today's talk is about a new force field called MINFF. It's MINFF. I call it MINFF because it's it's mine. But it's also sort of a general mineral force field. Hence, it's a new force field, but it can be used for very, very old minerals. Hence the title. Let's see if I can change slide. Great. So I just wanted to show and just introduce to everyone, if there's anyone who's not too familiar with the terminology, what's a force field in this context of molecular dynamic simulations or Monte Carlo simulations. So this is a slide from Michael Levitt. That basically shows a couple of equations that we can use to basically, in a very mechanistic style, describe the interactions within molecules and between molecules, so the intra and intramolecular forces and energies, basically. And we use these fairly simple mathematical expressions together with coefficients that's specific for different types of atoms, so-called atom types, to describe the energy and forces between interacting atomistic systems. So this is what I mean with a force field. Do we really need force fields for minerals? Are sort of molecular simulations of minerals, is that something that the research community is doing? So this summer I did actually a small bibliometric analysis of this field because it's typically not geochemists that is spearheading the research concerning molecular simulations. We're just a small community in a big pond of, I don't know, life science people and biochemists or structural biologists looking at protein chemistry, for instance, or lipid bilayer membranes. So basically, there's still a fair amount of publications each year that's related to molecular dynamics simulations, as I sort of focus on, and minerals. And we can also see if we also add clay as a keyword to minerals, we get clay minerals, and we can see in blue that there's still a fair amount of, but quite small number of publications related to clay minerals. And this is sort of my area of expertise. If we focus in on the clay minerals and add my favorite mineral, montmorillonite, we see that it's actually dominating the number of papers related to clay minerals. So montmorillonite is a sheet silicate that's quite interesting because it has a lot of natural charge defects, which creates a negative surface charge of these sheet silicates. And that negative surface charge needs to be counterbalanced by free counter ions, typically calcium, sodium, or potassium, as you can see on the bottom left. And we can have a number of these different types of montmorillonite and similar type of smectite clay minerals. I thought I would show a picture. This is what they look like in an AFM image from an atomic force microscope. And they basically are sheets, or we call them actually layers, that extend a couple of 100 nanometers in sort of the lateral dimensions, but they're only 1 nanometer thick. And that creates a really large surface area. So they have a specific surface area of about 700 to 750 square meters per gram, which is sort of comparable to a soccer field for 1 gram. So large surface area materials. And they consist of these, let's see if I can add a laser pointer. They consist of these layers that we call TOT layers. So the T stands for tetrahedral sheet, or basically silica, SiO. And so we have two of these T layers, and sandwiched between those are an octahedral layer that contains either aluminum, magnesium, or iron, uh, an oxide layer. And together, all of these sort of TOT layers form a 1 nanometer thick silicate layer. When it comes to force fields, traditionally, there's only been two really usable force fields. It's one of them is ClayFF, which was published 2004, and the second one was Interface, that's been sort of published and sort of incrementally improved upon a few times. And as you can see, ClayFF is a bit more popular. And actually, this is just the number of citations from this single original paper from number 4 in blue, whereas Interface, I've added all the citations from 3 manuscripts. So actually, ClayFF is quite more popular because I might have missed other publications related to ClayFF force field. And the reason for that, why ClayFF is so much more popular, is if we go to this slide, it's very simple. It contains, let's see if I can get this animation working as well. It's very simple. ClayFF is a non-bonded force field. The total energy of the force field is just the sum of Lennard-Jones potentials and Coulombic potentials. There's no bonds in this force field, except actually to the hydrogens, but I didn't include that. So there's an SBC-like OH bond, but I didn't include that. And that makes this force field very easy to set up because you don't really have to keep track of which metal to oxygens are bonded to each other, or do they have angles or dihedral or pair interactions. So I think that's part of why ClayFF is so popular. It's very easy to set up. Interface, on the other hand, is sort of the opposite. So in the interface force field, we have energy contributions from both the Lennard-Jones and Coulombic interactions, but also for all the metal-oxygen bonds, which also have angles. There's also some pair interactions that I didn't add here. And because we typically simulate periodic minerals, where these layers extend the whole simulation box over the periodic boundary conditions, it's a bit tricky to set up these type of simulations because you need to find both bonds and angles across sometimes triclinic unit cells or supercells. So, and there hasn't been many, because we're a small research community dealing with this type of minerals, there hasn't been a lot of different types of tools to deal with this. Anyhow, this talk is about the new force field, which I have developed in my group, and it's basically supposed to be the mean or the middle way of doing things. So what I include in my new force field is the Lennard-Jones, the Coulombic contribution, and the angles, the angle terms of all metal-oxygen pairs, but no bonds. What this allows us to do is to describe the coordination around the metal centers better. Because in ClayFF, because there's no angle terms and there's no bonded terms, metal coordination typically ends up being extremely symmetric. Whereas if you actually have an asymmetric bonding site and you add angle terms, you can describe that coordination site much, much better. So one could also, and in comparison to the interface force field, since we don't have bonds, we don't end up as having such a rigid type of force field or rigid type of structures as the interface force field. Because the interface force field, due to all its interactions, it's sort of extremely rigid, which is not good. So yes, some details about this new mineral force field. We don't use any actual bonds except for the OH bond, similar to the ClayFF force field, except our oxygens are compatible with the OPC3 water model, preferably, and not the SBC or SPC water model. And it's actually not a single force field, it's a force field family, because I have different subsets of atom type specific force field parameters for different types of angle force constants, where I have angle force constants, K angle, of 0 to 150, 500, and 1500 kilojoules per mole and rad squared. And I wanted to basically derive different force field parameters so one can actually test the influence of the angle force constants and the rigidity of the minerals. So there's actually four different angle force constants to choose from. So where the first one, where we basically have a zero force constant of 0, that's basically similar to KFF. And where the highest force constant is similar to interface. So we're sort of bracketing the space between KFF and interface. What's also new is the electrostatic charges of all the atom types in this new force field, where we actually don't have a set or a specific set or a finite number of atom types. Because in these force fields, especially if we're modeling morillonite or another mineral called nontronite, we can have up to 4 different metal sites within the same mineral. And all these metal sites are bonded to 4 or 6 different types of oxygen. So we can have a large number of different oxygen types. And it's really hard to come up with a fixed number of atom types for all these different types of minerals, because we can also have many different types of minerals. So what we do, and this is sort of inspired by KFF, we basically have an equation that allows us to calculate the charge of the oxygen as a function of the partial charge and the formal charge and the partial charge of the metal sites it's bonded to. So we basically use this equation on the fly when we're setting up our input files for MD simulations to calculate the partial charges of the oxygens. With the Lennard-Jones parameters for oxygen is taken from the OPC3 water model. However, the Lennard-Jones parameters from the metal sites were optimized using MATLAB routine, where we basically allowed an atom library that we have developed in my group to act as a wrapper and sort of a wrapper for GROMACS. So we can basically allow MATLAB to run GROMACS. And we use one of MATLAB's nonlinear least squares optimizer to basically optimize the Lennard-Jones parameters. So for these force fields, the observables that we targeted in the optimization process was the bonding distances compared to XRD structures, the angles compared to the XRD reference structures, and the unit cell metrics. And then, as I said before, it's a family of force fields. So, and actually, we have a general force field that was trained with over 30 minerals, and I call this sort of G MINFF because it's general, at 4 different angle force constants with oxygen and Jones parameters from the OPC3. But we also did tailor-made force fields for the same angle force constants for a large number of minerals, about 30, that basically has tailored Jones parameters for both the metal sites and the oxygen sites. So I'm not gonna go into too much details, but I did comparisons with the KFF and interface regarding both Lennard-Jones parameters, basically the atom type sizes and the van der Waals strength, but also the partial charges. And overall, what we could see is that there was a huge difference between the partial charges in KFF and the interface, the 2 previous force fields. Whereas for this new force field, the charges are different, but lie closer to ClayFF than interface. And the charges was calculated, as I said already, perhaps using CP2K simulations, and they were based on the CP2K simulations and the DDEC6 charges by Thomas Manns. And they're sort of similar to Bader charges, if you're familiar with that. The training set of minerals were that we used were basically based on experimental structures. Initially, I thought I would maybe go with DFT optimized structures, but I'm not a DFT expert. And when I was trying to get into different iron 2, iron 3 minerals, I started to get really inconsistent results, basically because I'm not a DFT expert. So I gave up that pretty quickly, actually. And what I found instead was semi-empirical way of basically ranking different types of mineral structures that sort of floats around in the literature. And I use a so-called global instability index, this G2 factor, for various types of structures. And this G2 instability index should preferably be less than 0.2, because that's the only type of minerals we can find in the environment. So what's this global instability index? It's basically based on the bond valence sum method, and it's basically a semi-empirical method. It's strictly semi-empirical, based on tabulated data for different types of metal-oxygen bond distances. And it takes into account not just individual bond distances between, for instance, aluminum and oxygen or magnesium and oxygen. It takes into account sort of the exponential sum of all the bonding distances per metal site and its coordination sphere. And it's just one way of sort of semi-empirically trying to check if a structure is structurally sound or not. Because if this global instability index is larger than 0.2, it's likely not a stable structure, because we don't find minerals with values larger than 0.2 in the environment. Okay, so basically, how do we do our simulations? A lot of the work we do, both in preparing and analyzing our data, relies on a MATLAB library that we have developed. It's called Atomistic Topology Operations in MATLAB, which is basically a modular framework with over 100 different separate functions that we use to basically build our systems, parse input, output files, do various types of coordinate manipulations, printing topology files. We can even use it to plot theoretical XRD structures. So it's fairly simple. One just sort of, since it's modular and since it has a fairly consistent sort of syntax, we sort of just we use different types of operations on the so-called MATLAB struct variable that contains, it's like a Python dictionary. So we can just manipulate molecules more or less any way we want. Regarding this, I used to share it on, and I still do share it on the MATLAB file exchange, but we sort of ported this recently to GitHub. And on GitHub, I also now have my force field parameters together with some documentation and also benchmarking data. I also have this now, the Atom library. What I've also started doing with a little bit of help on using sort of Copilot, so a little bit of help of AI, actually quite a lot, is I'm starting to port this MATLAB Atom library to Python. And I call this Python library AtomicPy. So atomistic topology operations in MATLAB in Python, which is a very bad title. So if you're interested, you can go and check that out as well. So right now it's sort of a lightweight library compared to the MATLAB library, but we're getting there. I also played around a little bit more. I added a ChatGPT tutor that can actually help you explain the MATLAB Atom library. I also have some more documentation on our group's website. I'm not sure. So I added some slides related to the MATLAB library. I'm not sure if it's super interesting. Basically, it can do various different types of operations on molecular systems that we need to set up in order to run MD simulations. And it's specifically designed to set up simulations of periodic structures and assign atom types according to the MINFF or ClayFF or interface force fields. So we basically use arguments like this. We can import a structure from an XYZ or PDB or GRO file. We can also write to different types of file formats. We can add water, we can merge atoms, we can translate, rotate, slice, we can calculate center mass. Yeah, a lot of different things. Because we use the MATLAB atom struct variable, we can also use sort of different types of filtering operations or using Boolean logics. So we can basically filter our molecules and sort of do different operations of different parts of our operation or molecules. We can add molecules to each other and update all the sort of molecule ID indexes and atom indexes. There's sort of functions for that. So, and we're now trying to sort of convert a lot of these functionality to Python. I know there already exist a lot of good Python libraries online, but I sort of, since we started writing our own library in MATLAB, and since it's very specific to certain types of minerals, it's sort of nice to also have a similar type of library and functionality in Python. So a typical, I can skip this basically. Anyhow, and what's new since this year, starting with the migration to Python, is that we now set up basically an Atom or Atomipy server that can basically do atom type assignment and printing of topology files. So if you go to this address here, atomipy.io, you can upload a GRO file, a PDB file, or a XYZ file. You can assign, not interface, you could, if you want to create an interface system, you could do that at the Charm GUI server online. But for MinFF or ClayFF, you can use this topology server. And basically, you can print GROMACS, Charm, or LAMPS topology files. So we typically run GROMACS, so I haven't really done proper testing with the Charm or NumD and the LAMPS data files, but they should work. They seem to be okay. I've done sort of single tests, and it seemed to work. What's also good with this server is that you get log files of your structures that basically lists a lot of different properties for your molecular system, not just supercell size and weight and stuff like that, but it should also contain the total charge so you can check that you get the charge that you sort of intended. It also contains a list of the contents of your simulation cell with the different atom types, the number of different types of atoms, the charge of the different atom types. What you also will get is some bonding and angle information. So here it's important to realize that individual atom types can be bonded, since they're bonded to different types of, let's say we have an aluminum here, we have an octahedral aluminum. It can be bonded to different types of oxygens. So we can always, of course, sort of calculate some sort of coordination number. It's 6, makes sense. and some average bonding distance and some average angle. But what we also want to do is look at atom type pair specific bond distances and angles. So we get that as well, because an aluminum oxide average distance might actually not say much if you want to do comparisons of a simulated structure to experimental structure. So we really do need these atom type pair in bonding distances and the corresponding angles. So I think this is the first example I've seen of this. Cool. I'm just going to go through some results from the force field optimization process. So the reason we wanted to test what happens when we add angles is that we typically prefer to use ClayFF, as most people in the literature, and ClayFF is pretty good at reproducing unit cell metrics, but not the actual positions of the atoms within the unit cell, because typically the coordination geometries around metal sites becomes extremely symmetric because there's only electrostatics that govern the interactions, whereas most minerals have a symmetry in them. So we needed to add angle terms to better represent the asymmetry in minerals, basically. So we did a lot of simulations as a function of angle force constants. And we basically realized that, yeah, of course, we get better agreement to experimental structures the higher angle force constants we get. But there's typically sort of some just because we sort of turn up the angle force constant, we don't always improve all the parameters at once. And what we also saw, and I'm not showing you any data here, that we basically affect the sort of Young's modulus of materials and other types of elasticity coefficients. So we don't want to turn into sort of interface force field that's heavily sort of constrained. And when it comes to results, what we saw is that even if we compare for ClayFF, and this was actually one of the sort of initial results that sort of convinced me that I should try to start this work designing a new force field, because ClayFF was actually designed and optimized for a particular kaolinite structure. So when I calculate the theoretical XRD pattern of this kaolinite unit cell from BiSH 1993, I basically get this red curve here, and the blue curve is for ClayFF. And we can see fairly high discrepancy with ClayFF. And this is kind of interesting because this was the particular mineral that ClayFF was optimized for. So basically what we tried to do then, we tried to see if we could come up with a better structure. So this is sort of the tailor-made MINFF, and you can see we have much better agreement. Not perfect, but much better. We also looked at power spectra, and we did a lot of experiments as a function of angle force constant. This is a bit too busy to go into, but we basically see that if we turn on the angle, if we use angle force constant of 250 or 500 kilojoules per mole and rad squared, we get fairly good results. Whereas if we go to 1500, we typically don't get very good results. Typical simulations that we do in our lab is basically dehydration simulations, which you could see here on the left-hand side, where we basically incrementally remove water molecules throughout the simulations. After equilibration, we equilibrate these simulations for a couple of nanoseconds, so they're sort of nicely equilibrated. These are really nice experiments because they basically probe clay swelling or clay hydration and dehydration, which is something we can measure, for instance, with X-ray diffraction. And these are also very interesting simulations because we get a ton of different data from them. We can analyze countercation density, So this is a busy figure on the right-hand side, but it basically shows you density profiles as a function of water content. We can look at system electrostatic potential. We can analyze ion diffusion or water diffusion. I wanted to say this is a type of simulation that we typically do when we want to study new sheet silicate, because we have a lot of these simulations now for different types of minerals under different conditions. So right now we're doing these type of simulations for not montmorillonite that I talked about before, but for a similar type of clay that's called nontronite. That's is a frequent smectite and supposedly common smectite clay on Mars. So I of course wanted to show some performance when it comes to running these simulations on GPUs as well. Um, um, so basically what this busy diagram shows is the um, nanoseconds per day that we can get for different types of water layers. And the water layers doesn't tell you anything. But what you can see is that if you go up to 6 water layers, our system contains about 10,000 atoms. So that's a very small system for most people doing MD simulations. But for me, it's a pretty big system. Whereas when we dehydrate the systems, we end up with only about 3,000 atoms. And that's basically just the clay lattice atoms and the ions. Because we're shrinking our systems, these type of simulations was historically a bit tedious to run on CPUs. No, yeah, on CPUs, because when we had large systems, we wanted to run on large number of CPUs, but when we had fewer numbers, we wanted to run on fewer CPUs. But so they were hard to run automatically in a single run. So we don't really have this problem anymore with GPUs, because GPUs are much more stable and can handle these different types of simulation systems that have very different types of sizes. So previously, we have also been running a lot of simulations on our own GPU cluster here that we have. We have a few different, basically consumer grade computers with RTX 3080 cards. What was interesting when I was running these 3 different force fields, ClayFF, MINFF, and ClayFF, interface, and MINFF, we saw that I thought they would have a bigger discrepancy. They're the sort of grayed out data points here. That's not very interesting because they have either no bonded interactions or a lot of bonds and angles. But we can see, at least with GPUs, that sort of performance is not that different. Although the performance changes a lot from simulation to simulation, just because we change the water content or number of particles in the system. That's a bit interesting. But currently, so what I've been testing at Kebnekaise is the L40S GPUs and the V100. And as you can see, we get best performance with the L40S here using 2 GPUs. I didn't try with 1 GPU. Well, I did actually do a test, and it was much lower. The red curve shows the V100 with 2 GPUs, and the green one, the V100, with only 1 GPU. And you can definitely see sort of what sort of gives the best performance. So it's quite interesting that the L40S is so much better than the 3080 GPUs. I was at least astounded that it was such a big difference, especially for the big system, because then it's a factor of 2. And this is with 1 femtosecond time step. So I can do, since I do small systems, I could do really fast simulations, basically. When it comes to the specific commands that I use in my job scripts, this is sort of the interesting part, maybe. I use 2 tasks. I don't define the C parameter because I'm not sure I need to. And I either said like two GPUs, but if I want to run on specific GPUs, I pick for instance the L40s.
Mm.
I use the latest sort of precompiled version of GROMAX on Kebnekaise, which is compatible with the GPUs. The only thing that I added that wasn't in the documentation was this bonded GPU flag,
Mm.
which increased the performance substantially, at least for me and my type of systems. Um, okay, so I just sort of introduced some performance data there
Mm.
because of today's audience. I I I have a few more slides, but basically the reason we wanted to do this new force field and the reason why we sort of need to do simulations of these type of systems are many, but the reasons why we came up with this force field is basically because if we look at the original structures of sheet silicates, they have a basically silicate structure that looks like this at the top left structure here, where you can see that we have asymmetric holes in the sheet silicates. Whereas if we run with ClayFF, we have sort of very hexagonally sort of and symmetrically shaped holes. So if we turn on angles, we can reproduce the experimental structure much better. And I'm not sure if we want to see more results of that type, but we also did sort of density mapping to see what's the difference between ClayFF, MINFF, and interface because they have different charges and blah, blah, blah. But what I wanted to get to is that as we also have uploaded on GitHub, we had a lot of benchmarking data there that shows either how the force field behaves in comparison with ClayFF and interface, not just in general, but for specific minerals in the terms of unit cell metrics for the A, B, and C unit cell vectors and their angles, and what global instability indexes those minerals have. And also we compared distance or bond distances and angle differences. And in general, we can see that MinFF behaves much better than ClayFF for most minerals. Some minerals, ClayFF is really good. And when it comes to structural properties, we're almost on par with interface. However, we're not modeling as rigid minerals as interface. So we have typically better Young's modulus and more experimentally sort of elasticity coefficients that agrees better with experiments. Um, so to summarize, by adding simple angle terms, but no bonds, we can improve sort of uh, the improve bond distances and angles to mineral simulations. Um, how well this is in reality is specific to different minerals. And we have on GitHub, I think about 45 different minerals with unit cells and input files that one can use to start simulations. And we also have benchmarking data for all these minerals and for all the different force fields, the general MinFF and the tailored mineral FF force field. Um, and then, yeah, lots of documentation on GitHub. And then we have the topology server. It was kind of this whole project has taken a long time because, for one, it wasn't funded. It was a side project. And for the second reason was that it was kind of hard to figure out what would be the target observables. What do I want to optimize? Because I'm sort of an inorganic chemist or geochemist, I look at the structure of minerals. So looking at the unit cell metrics and bonding distances and angles is sort of what I'm interested in. But other computational chemists, especially sort of doing life science or organic molecules, or even sort of more sort of in a physical sense, material science, are more interested in energies and forces and use DFT-based training data sets. Whereas me, as that I also do XRD, I prefer to do sort of use XRD reference structures as a training set. And anyhow, so right now, sort of in my sort of small benchmarking data, I sort of come up with the L40s are the best so far, especially if I add this bonded GPU flag. Um, I think that's all I had. Um, so I have two PhD students that work with simulations in my group. I have another one that's an experimentalist as well. And we do different types of simulations, but mostly molecular dynamic simulation with GROMACS. Um, and they've also been part of developing this mineral force field to different extents.